Thank you, Marcus, and thank you, Canton Coders, for having me. I always enjoy working with Canton Coders. You guys are really cool. And I'm going to share a few things. Now I have to, excuse me. Let me find my Zoom. We're having technical problems over here. Okay, I'm going to share my screen here a second. And here we go. Whoops. Now, is that, are you, that should be.
Yep.
Okay, here we go. So does everybody see this now? Is that all good?
Yep.
Okay, great. Again, thank you. This is me. And besides playing Dungeons and Dragons, as he mentioned, I'm an Agile coach. Here's ways to contact me. There are some slides that you might be interested that I keep on SlideShare on other technical and other Agile process matters. I also keep interesting things in my LinkedIn, and you can always contact me by email. Anyway, I did. How did I do that? Oh, you only see my name. Well, let me see. I was just trying to share the screen. I'm not sure I can do both. Can we just go on anyway?
Sure.
Oh, I see. It's I had stopped video. I did not mean to do that. Okay. Now we're going to go back. All right. Here we go. Restarting. Okay. So this is all about testing and what they didn't teach you in computer science class. So we've got a couple folks on Zoom as well as people on Twitch and YouTube. For the folks that we can hear on Zoom, what is your experience? What did they teach you about automated testing in undergraduate computer science? I hear crickets.
Nothing.
Well,
I mean, that's your answer.
They taught you that test was something you did during midterms and during finals.
All right. Yeah. Testing something you did in midterms and on finals, not something you did with your code, huh?
No. That's extra lines of typing.
That's extra lines of typing. Okay. Well, you should be testing. And why? Hang on. Because among other things, it saves you time, money, and even lives. So anyone spend any time debugging? Crickets? No one ever has to debug?
I've been a developer for 25 years. I've probably been debugging for about 10 of those.
And that's pretty common. So debugging is a really painful process. It takes an enormous amount of time. It is not efficient. If you write tests, you spend a lot less time debugging. Writing tests also creates the code that is loosely coupled. And if you don't write code, you tend to end up with this mess. And not just the mess we see on the right-hand side of code that is long and goes on forever, but even on the left-hand side. By the way, those are all microservices, but that's a network diagram, a network graph, dependency graph of how all of those services connect to each other. That's an enormous mess. Testing solves a lot of those problems because you have to be independent to be able to be tested well. So not writing tests is also expensive. One of the more well-known problems with not writing tests is that Knight Capital Computers. In 2012, in less than an hour, Knight Capital Computers executed a series of automatic orders that were supposed to spread out over a period of days. But that's not what happened. Millions of shares changed hands, almost instantly. The resulting loss was nearly 4 times the company's 2011 profit, crippling the firm, and it brought it almost to bankruptcy. The only reason they didn't go into bankruptcy is because a bunch of investors swooped in with $400 million lifeline. Fixing that error cost them $500 million. My personal worst experience was when I was working for a networking company, and we were supporting a network for a great many banks in Germany. One of our field engineers late at night tried to use his ATM, and that didn't work. So he went to the next German ATM, and that didn't work. So he went to the next one, and that didn't work. After the third one, he called the Network Operations Center. The NOC had just added the 256th node to their network. Anyone can guess what the problem was? Come on.
They hard-coded the nodes.
Well, yeah, but it was a byte boundary error. I was half asleep when I heard about the problem, so it took me about 30 seconds. It took one of my engineers about 10 seconds to figure it out. But fixing it took us 3 months. First, we had to reproduce the error in our lab, not so bad, write a patch for it for embedded software, burn that patch onto EPROMs, solder those EPROMs onto boards, ship the boards to Germany. This was when East and West Germany had been combined, and the roads up to the nodes were up mountains that were like goat tracks. And then all of them had to be installed in the 256 different nodes. 3 months of work. Non-writing tests also cost lives. Luckily, I have not been in this particular situation. The Therac 25 was a radiation therapy machine that had a hardware safety feature. And then they replaced it with software. A race condition caused over-radiation. And that resulted in debilitating injuries and 3 lost lives. Writing a test could have solved that. Writing tests also enables your software to be better designed, because in order for software to be testable, it has to be loosely coupled. And when you do that, it's more enhanceable. Those tests make it safe to refactor and keep your code clean. They also are an absolutely critical part of DevOps to make our modern systems work and deploy quickly to the field. So we start off with software that's really fairly straightforward. And then we add to it and it becomes more complex. And more complex. And more complex. Until it's a great, horrible mess. And the cost of change is enormous. If instead we write tests for our new features when we create them, then we have a little bit of a mess. But with those tests, we can refactor and clean up the code and keep that mess down. Anyone ever run into the "it works on my machine" problem?
Yep, all the time.
Yeah, well, automated tests and good environments solve that. First, we make sure that we've got a good CI system in place. And then we also make sure that we've got other test servers that simulate or create as close to the actual production environment as possible. In the cloud, that becomes a whole lot easier. So testing, and particularly agile testing, which is what I'm mostly talking about here, provides feedback, which is critical at a lot of different levels, down at the unit level, and then all the way out to end users with A/B testing. By the way, any of you ever use Netflix?
Occasionally.
Yep.
Yeah. Okay. So
I love Netflix.
one of the things Netflix does is it does A/B testing. It puts out a new version of its software and it rolls out part of it to one group of people and part of it to another group of people. And then it takes metrics on how those different users use it. And from that feedback, if it's makes their life better, i.e. they get more clicks, more people are interested, and therefore eventually more money, they keep it. If not, they remove it. So they get enormous feedback. So how does this work? Well, this is how it doesn't work. But if you are in an environment that's a large company, you probably have remnants of this waterfall system in place. Most businesses don't call their systems waterfall anymore, but you're probably got some of it anyway. And what it lacks is any kind of useful feedback. So what you want is you want code that's tested, but writing that test after your code, and we're talking automated tests here, desk checking does not count. It is not a unit test if it isn't automatable. Tells you about bugs you have after the fact. That's not very good. What you want is a test that will tell you about things ahead of time, and then you get a virtuous cycle of feedback. That short cycles are what makes all of this work. Now we have a little of our code tested, but our design is somewhat questionable. Let's bring that into the loop. Again, we want more feedback, now short cycles, and we can test how our design works. And as you're doing that, that's part of what we do with refactoring. We're constantly looking at it. But what we have here is that we have some requirements that came into us. We implemented them, but then later we found out that wasn't what they really wanted. So again, let's put those into that loop. And we'll go into some details on exactly how you do this as we go on. This is called behavior-driven development, where we actually write our automated tests for our requirements first. The previous bit was test-driven development, where we write them for our code before we write it. Now, we may still have problems because we thought that was what the customer wanted. But then when we actually got it to the market, that wasn't really quite what they wanted. So if we can deploy those and get some feedback on it, then we get better working. Our marketing department is happier. But are they right? Is that really what our end users wanted? Well, is our vision correct? Maybe not. Maybe our business vision was the wrong thing. With that, we can actually test what we are putting out to the marketplace. And that's where things like the A/B testing comes in. This is part of what's called lean startup. And it gives you an enormous amount of feedback on whether or not something is really useful out there. Most all of these processes are automatable.
Hey, Camille,
Yes.
I'm just going to jump in here. We have a question on Twitch. The question is, what do you tell management if some coders finish their work faster because they're not writing tests, which makes those who write tests look slow?
Thanks, James Simon, for that question.
Well, you tell your manager, would they rather get problems out to production and then have their end users tell them that things are wrong? Or would they rather spend a little bit of extra time up front getting those tests in place? And if you look at the amount of time that the developers spend actually working on it, including the amount of time they take to fix bugs, writing the test is faster. If you're only counting the time that they wrote the code and they're just throwing it over the wall, then no, it's not. But they're not done if you just throw it over the wall. They are falsely assuming that they finished when they haven't. That's what I would tell managers. And there are plenty of statistics out there, and I'll show you some examples. There's a good book that goes into some details about what happens when you do that versus what happens when you don't. I'll have a couple of slides from it, you'll see. Did that answer the question? Yes, no, maybe?
Maybe.
Maybe.
I haven't seen a response.
Okay.
Yes,
Anyway.
it was answered.
So, so we write tests, of course, for ourselves. I don't want to spend my time debugging. I don't want to spend my time getting calls in the middle of the night for a production system that has crashed and that I need to fix. Neither does my team. Other devs that use our code, they would like to have tests in place to make sure several things. One, that our code is reliable. Also, it informs them how to use it. Anyone who has to maintain your code later, tests are for them. Lots of other stakeholders too, like your security folks, production support, call centers, managers. If you've ever rolled code out to the marketplace and then had to support it yourself, and that happened to me at one point, I was one of the team leads on MCI Mail. That was the first commercial email system. This is before Yahoo Mail and Gmail, and that the only general email systems out there belonged to the military. And we had to put that out a month or two earlier because of various things happening in the marketplace. It rolled out, it was not tested. And then I went out and I had to support that. I tell you, it's painful, it's embarrassing. You don't want to be that person. You don't want to have other people in the call centers or doing the production support that are that way either. So write tests, make your code reliable. And your company or organization. We've shown you a couple of cases where people lost amounts of money, sometimes lives, company reputations. Number of firms and organizations have gone under because of bugs they could have caught in their tests. Or they get code that's so complicated to fix and change that it just becomes useless. There's one case that I know of, I believe it was, well, actually, I don't remember what language it was written in, but for every 3 lines of code that were changed, the new bug crept in. That becomes completely unusable. Or at least you can't add anything new to it. And then, of course, our end users. That's who our tests are for. Now, what type of tests? Well, in general, we have tests that we want to have that will have a business focus. There are going to be some other tests that will have more of a technology focus. Some of our tests will support the software development itself, and others will critique the product that we built. Most types of tests should be automated. There are a few that should be manual, and I will mention those. There are not many. So this is testing quadrants. If you haven't seen that before, Brian Merrick invented this basic concept of how to look at software. Everybody modifies this a tad. The 2 types of tests that you absolutely need to do manually are usability tests, unless you're developing, say, a heads-up display for fighter pilots, because there they have machines that actually track eyeball movements. So even interfacing with the human in the testing process is automated. But for the rest of us, we need a human in the loop there and another human checking how that's actually working on usability. Exploratory testing is another thing that there are some testers, traditionally manual testers, although more of them are getting automated skills, that are extraordinarily good at finding things you just might never find otherwise. Once you do find them, you should write an automated test for it. They're sort of happy paranoids, like Secret Service agents that are not looking at the president giving a speech, but are looking at the crowd for who is trying to shoot the president. These exploratory testers have, and good testers are great. And A/B testing is partially manual, that is, there are users out there using it. And there are also a number of tools like Google Analytics, for instance, gathering stats. The rest of it all should be automated to one degree or another. The part that is both technology facing and critiquing your product, like security testing, load testing, scalability, etc., performance, those you can use tools for. So yes, you want to forecast what you think that your usage is going to be, but you also want to, as much as you can, test what it's actually going to be. That horrible waterfall process with the testing all at the end, that's what healthcare.gov used. And that incredible mess of where absolutely nothing worked when all of a sudden real users needed to get online and use it quickly. In contrast, Connecticut and Kentucky built their own systems using agile practices, and they were extremely reliable, including lots of automated testing. So in the business-facing side, we have behavioral testing, behavior-driven development, characterization testing, which we'll talk about a little bit later, and some others. When we get closer to the developer, there's, of course, various types of unit testing, in which we'll talk about test-driven development, and integration, and component testing, and so on. But there's a different ratio of these tests that you want. This is what you don't want. Often called the ice cream cone, and I don't remember who actually invented this term. There are a lot of organizations out there that do a great number of manual tests. They take forever and they're hideously slow. Those organizations have a very small number of unit tests. This is the opposite of what you're looking for. What you're looking for is this. You want a lot of automated tests, mostly unit tests. Then you want some integration tests. And right now I'm talking about the product developer side, not things like performance testing. You want some business-focused tests with the behavioral, and you may want a few automated GUI tests, not a lot, and just a tiny bit of those manual testing for the exploratory and usability.
Camille, regarding the GUI test, there is a question on Twitch asking if you're going to speak to automated UI testing.
I will speak to it briefly right now, which is don't use capture playback. Capture playback is extremely brittle. If you're going to write those tests, do it the same way you do with the other ones, and that is write those tests first. There's some good tools that you can do that with, but you don't want very many of them. Mostly, you want your tests just below the browser or whatever your UI is, but there can be a reason to use a few of them. I've written some nice ones using page object and Gherkin and Cucumber together to do automated GUI tests. Perhaps at another time I will demonstrate that process, but you want very few of those. Why? They're extremely slow. The other thing about GUI tests is that they tend to be brittle, depending on how you write them. Page optic less so. Capture playback absolutely breaks all the time. Because in the capture playback version, if you move a widget, it breaks your test. So at the top here with the painfully slow, we're going all the way from the user through the web to the servers, through the network to the database, and all of those things, and all the way back. So that's really slow. The automated unit tests, they're lightning fast because they are very isolated. We'll talk how to write those. And we'll be talking a good deal about things at the unit and the BDD level.
Camille, we also had another question come up about the previous slide from Curious Agilist, asking for the reason behind the ice cream test pyramid, why it happens.
Why it happens? Well, first of all, once upon a time, I go back forever in this field. I started coding in 69. There weren't any automated tests. So what people started off with were manual tests. And right then, our code was really small, so we could generally desk check and get away with it. As things became more and more complicated, code became harder and harder to manually test. Also, remember the testers I told you that are really useful members of your team? Most of them don't have the skills yet to learn how to write automated tests. Bring them into your team and teach them automation. They can teach you things about testing you didn't know, but together you can really be great. But so a lot of that's just inertia. That's the way it used to be. Some of it's that people lack of knowledge. Some of it is new skills people need to acquire. And also, I think, a lack of awareness of the cost of testing. And I'll discuss that in a second. So here's where these, did that answer the question?
I believe so.
Okay. So here's where some of these tests should run. First of all, as you're writing your code, it's going to run on your desktop or laptop, whatever you're using for the most part. And with that, when we're running the tests, run all of the tests, at least at the unit level. Some of those other behavior tests are slower, and you may want to run those a little less frequently. Then the tests will run on the continuous integration server, performance, security, other servers, test servers. All of those these days can live in the cloud. And that means you don't need to spend money to buy pieces of hardware that only run sometimes. You can spin them up when they're needed. The CI server you probably want all the time. The other ones you can do on an as-needed basis. Here's how that cycle works. You're a developer, hopefully pairing or mobbing with a team, but in any case, you run your tests locally, make sure they're working, all of them please, and you check them into some version control system. Those changes are monitored by the CI server, who will update your build, assuming the software is compiled, and build and run tests. Then it in turn will send a build report and a test report about how that went. Generally, when you set this up, you only want to receive issues for problems. You don't want to hear about everything going right. Then from there are a number of, once you have a good clean build, which could be happening every few minutes, you may be running into other servers. Right now, I'm just, for testing, right now I'm just talking about the performance and security and various types of test apps, but you could have other things in there that are integrating with other groups of people that are writing software. So you could have a whole sort of chain of these. Then finally, that can get deployed to your deployment server. Some companies, this last step, they want to make sure that it's a manual decision on whether to go live. Others do it automatically. For example, Amazon deploys something new every 11 seconds. Now, this refers to testing in general, but specifically mostly to unit testing. There are two approaches to writing tests. One is what you call black box, where those tests, you have inputs and outputs in both cases, but you do not know the insides. You assume that you don't. And if you're writing your tests first, which I strongly recommend you do, you don't know what those are. The other approach is what we call white box testing, where your tests know about and are dependent on the internals of your code. White box tests break a lot and are generally no one tends to maintain them as a consequence. So if, for instance, you had some internal structure you were maintaining with an array, and you decided that you wanted to change it to a stack or a ring or some other collection class, if you wrote those from a white box test, as soon as you changed that, A would break. You don't want that. So don't do white box testing. If you write your tests ahead of time instead of after the fact, you won't be doing white box testing. Test-driven development has a virtuous cycle. You write a failing test. You write a test, and because you have no code for that test, it fails. Then you write just enough code, not lots of extra code, but just enough code to make that test pass. If you do this a while, the code gets messy, like we saw in the messy diagram. But that's where you go in and refactor. And because you have those tests in place, and because they're testing the behavior, you know, not whether you're using a ring or an array or what have you, those tests will continue to keep your software safe. So if you break something while you're trying to refactor, you'll immediately know and you can fix it. It's also much, much easier to fix things that have a very small delta from what you just wrote than it is for a large one. So this is all about doing it in baby steps. We check in frequently, and we have an opportunity to deploy frequently. With this, we enforce loose coupling because that's the only way you can write this kind of code. And adding features becomes simpler. This is in contrast to what's called verification and validation, an older technique which comes from the waterfall world and is still used, where testing and many other things are at the end. With that, when you test after, you can get a false positive. Things can pass for the wrong reasons. That means if there's something in there that's wrong, you don't know about it. It's much harder to write these tests afterwards. And there's never enough time. Fixing bugs, because there's such a huge delta between what you knew was working and what you now have, is a nightmare. Behavior-driven development focuses on the business side of things, and it's similar in concept to test-driven development. Here, where you can use things like Cucumber with Gherkin, or in the unit test and the TDD stuff, NUnit, JUnit, etc. And you write some red tests, that is, tests that don't pass, before you write the code to implement them. For this, you want an active product owner or product manager or customer rep or whatever you call this person, who has that business knowledge. And you together, you sit down with them and you talk about what those should be. What should be the acceptance criteria? This creates an unambiguous specification. It can't be vague because you can't write automated tests to something that's vague. Because it's not vague, you know if you've got it right or wrong. And because it's automated, it is automatically documentation. And it's readable documentation. We'll show you a couple of examples a little later. It catches broken features and it proves when you're done. Adding features is much simpler. In contrast, when you do all of your tests afterwards, you don't know that your requirements were too vague until it's too late because the code's already been written to the wrong specs. And you never really know when you're done because you know that guy that you were mentioning earlier that got all his code written, he wasn't done. He just didn't know it. Often this type of test after is manual and it can be arbitrary. The testers can, if you have a formal team of testers, may come back and complain about things that really aren't relevant and miss things that are. There's never enough time. Bugs go undetected. Again, it's a nightmare. So given that, how do we test? First of all, wherever possible, do not use manual tests. You don't have the time. For your first iteration, you write some new features, you have time to test them all. Maybe for your second. Once you start getting, you know, several iterations or releases together, you lose the time you need to test them if you're doing it manually. Because you only have a fixed amount of time. And because of that, you break features you don't know you've broken. Bug growth increases over time when you're doing manual. If you're not doing automated regression testing, the only way for this regression testing to be doable in the amount of time is if it's automated. So if you don't automate it, regression testing is testing all those things that you already created and that you'd like to still be working and to make sure that they are. So the ones you did in prior iterations or releases. If you don't, you get into this code and fix cycle. And over time, it gets worse and worse and worse. The more you delay the time between the development and the testing, the harder it is to fix things, the less you remember about what you're doing, and the more there's pain. Even in the best case, if you test after the fact, you have delay, and that costs you. The more you test, the less time you spend on fixing things. Debugging is a whole lot slower. As developers, we're not paid for typing. We're paid for thinking. So how fast we can type that code is not important. How fast we can actually get workable features out to market. We've got to look at the whole life cycle here. Again, the more time we save, the better. Test-driven development and behavior-driven development will test our code, particularly in test-driven development, every few minutes. In behavior-driven development, since we may be going through the entire system, it may be a little less frequently, but it should still be multiple times a day. Now, every type of test basically has three parts. You have the part of the test where you're setting things up for the test itself. Formal testers call that a precondition. If you're using one of the behavior-driven tools like Cucumber, it's often called given. And Java often calls that a range. Other languages use a different one, different terms. Then, now that we've got our software set up for our test, we need to do something that we expect to have some type of result. some type of action. And that's when we do something. In Java, that's often called act, as in arrange, act, assert. Then we need to compare, because now we should have some sort of positive effect from that, that what we expected to happen was actually what did happen. So those are our expected results or our preconditions. It's then. So we given something, when we do something else, we expect this to happen. We do use, in Java, we use asserts. It might be an expect in some other language. It all depends what you're using, but the same concept apply to everything. This is even true in manual testing. So behavior-driven testing, we're going to go look at that a little bit closer. First, you need to collaborate to build this with your developers, with people that have a testing hat. There may be other people that have specialties in particular tools or domains or what have you. And together, you and the business folks and the devs and them, whomever, come up and you talk about some stories you may have. Perhaps you created these stories using story mapping. Excellent technique. But we're not going to go into any detail on that here. That helps get you a minimum viable product. From that, then we now want some sort of acceptance criteria. And here we can look at a couple of high-level concepts of what we want to think about. From there, we can turn those into executable tests if we have the details we need to make that happen. And those executable tests can be run automatically. In this particular case, the tool I'm using, it actually shows nicely green when the tests pass. If they're red, that piece of the test failed. By the way, this is from a challenge in the real world. At least the conceptual part of how we're thinking about it was. Now let's look at an example and go into it a little more detail. So I assume everybody here has used an ATM machine at one point or another, right?
Yep.
Yep. Okay. Yeah. So you withdraw cash, you deposit checks, you transfer things to savings or checking, went back and forth. Let's look at one piece of it and how we might expand that into some good behavior tests. So let's look at cash withdrawal. So in order to get money from the bank is closed, as a bank customer, I want to withdraw money from the ATM. Okay, that's pretty vague. So let's think about some smaller pieces of it. There's cases where we have a successful withdrawal. There's more than one type of that. Say something less than the balance, equal to the balance. Those might be different. You know, maybe you want to warn them when they've taken everything out. Maybe you want to close the account, what have you. It might depend on what type of a system it is. Lots of failure possibilities, withdrawing from insufficient funds, cash dispenser didn't have any money in it or not enough. You know, the account was closed, or maybe there was a lien on it and it was whatever. That's kind of your first cut. Those are your high-level scenario titles. Now let's take one of those, like the success one, and drill down into that. So given my account has a starting balance of $100, when I withdraw $20, then $20 should be dispensed, and the ending balance of my account should be $80. That is actually code. Executable code, we'll look at the various pieces of it. And the important piece about this, to think about it, besides the given, when, then, and some words that are English language like, so that the business people will actually understand them, is we've got concrete test data. And we need that. Instead of saying, given I've got an account, when I withdraw money from it, then I should get the money I asked for, and my balance should be handled accordingly. That's way too vague, but that's sometimes how you get requirements when you don't look for the details. Now here is an example where we actually took some of those with our friends at the Code Liberation Front and actually wrote some tests. This is real code. This actually executes using that same concept. In order for that to work, okay, so this piece is in Cucumber. This is called Gherkin, and this is the English language style piece that basically your business folks can read. And you can collaborate with them on what should be in this part of it. Cucumber comes in lots of different varieties. It's free. If you're using C#, it's called SpecFlow. Most everybody else calls it Cucumber. And the business language part's called Gherkin. Then that needs to somehow connect with what the real code is underneath. And for that, we have something called step definitions. The implementation of this is different in each language. The first version of this was written in Ruby. This is the Java version, which is also quite popular. So you see the given, when, then steps we have here. And then you can see that we've got some Java code underneath that is actually going to be accessing the code we're looking at. And of course, the classes that we're implementing. So the test-driven development is, well, any questions on that?
We do have one from Jitter Ted on
Okay.
Twitch asking the step tests are where I find low ROI. What does Camille think?
It depends how you write them. Write your step definitions well. And so one of the things you need to be careful about is how you word your given, when, thens. Okay? And if you word them well so that most pieces of it are reusable, you can get a lot of reusability of it. There are a couple of good sources on how to write good Cucumber and good step definitions. But if you're finding that you have, for all of your tests, that something does something very, very similar and is using different wording, and therefore you've got different step definitions for it, then that's something that you need to refactor out. This is one of the reasons that I do not believe, as some people will suggest, that your business people should just go off and write their Gherkin, that is by themselves. They need some guidance. And you need to talk with them about how to make the language that they're using reusable, because the computer doesn't know that one given is actually exactly the same as another. It's just using slightly different words. So anyway, there's some good guidance on that. I will get you some references afterwards and put them in Twitch or Slack or wherever people would like them, to give you some good ideas on how to make that more efficient. Hopefully does that help?
Yes.
Okay. But it's not as trivial as it looks. There are some things you need to do to make it some smarts. The process of test-driven development is conceptually very similar. As I said, it's all about feedback loops, but it's at a much, much lower level. And we do everything in baby steps. We write a tiny test. We watch it fail. We only write enough code to make that pass. Now that we've got that code, we watch it and it passes. Or we fix it if it doesn't, and then it passes. And then if the code gets messy, we refactor in baby steps and we repeat. Again, write a tiny test, watch it fail. Only enough code to make it pass, no gold plating here. Watch it pass, refactor as needed, repeat. Write a tiny test, watch it fail, write just enough code, watch it pass, refactor is needed, and repeat. So here is an example. This one's using Python. And here we are implementing a code kata for coin changer. This is my particular version of the coin changer kata, where you are looking for only the minimal number of coins. We have some code working here that will return 1 penny if what we're looking for change is 1 cent. Now we're going to add a new test that for 2 cents, which should of course return 2 pennies. The code doesn't do that yet. Oh, this is in Python and PyTest, by the way. So we watch it fail. Again, by watching it fail, we know that if we get it to pass, the only reason it passed is because the new code we wrote. No false positives. And we see that it does fail in exactly the way we expected. So now we write some more code so it'll pass. And this is a baby step. You might want to be tempted to jump in and say, hey, I can solve this. Don't do that. Do it in little tiny pieces. This takes practice. In theory, it's easy. In practice, it takes a lot of time. In theory, there's no difference between theory and practice. In practice, there is. It's a Yogi Berra quote I like. For those of you who follow baseball or ancient baseball players, I guess these days. And here we can see that the tests pass. Okay, that feels good. By the way, this cycle starts to feel really good once you get used to it. It takes getting used to. Here is an example of tests in JUnit. There are hundreds anyway, of unit test tools out there, most of them free. There wasn't a free one for COBOL. A friend of mine, Dave Nicollet, was working with some developers up in Chicago, really, really smart developers who happened to be working in COBOL. And they wanted to learn test-driven development, but they couldn't because they didn't have a test tool. So he wrote one. This is free. For those of you who are working in legacy systems, it is possible to find something out there. Anyway, if you can do it with COBOL, you can do it with anything, pretty much. Now, what about bugs? Okay, you've got a production bug and someone is screaming at you to fix it. This is an ideal time to start using TDD, but it's a little bit less than the ideal of, hey, we prevented the bug in the first place. The bug is already out there in the wild. But we know what the behavior ought to be because somebody pointed out that we have an error. Okay, we know what the code shouldn't do. We know what the code should do. So we write a test for what the code should do. Now, because we've written that test, we now run it, and the test should fail. How many folks have ever fixed a bug and then sometime later found somehow it snuck back in? Any of the folks that have been out there a while experienced that?
Yep, multiple times.
Yeah, more than a few times.
More than a few times. You write a test.
Same bug.
You write a test for that, and it doesn't sneak back in. When you modify code, sometimes you change things you weren't expecting to have the side effects you did. If you've got tests in place, you catch that. So once you have, if you do test-driven, if you use TDD nowhere else, use it here. Because there is nothing worse than finding that bug hitting you in the face again. Now, these tests usually actually need to be written in something other than a unit test tool because you usually don't know exactly where the problem is. Now, in the case that I told you about the banking system, because we could just figure out, hey, it was a byte boundary problem, then we just needed to look for the place where it was checking how many nodes there were, and that when you added one, all of a sudden it went to 0, which is what happened, then you might actually know where the code needs to be fixed and therefore know where to write a unit test. But most of the time you don't. Most of the time, particularly if you're working on legacy systems, and we'll get into what to deal with legacy systems in a moment, you are going to be in a situation where you need to write your test at probably a higher level. So this would be a good time to use Cucumber or something or other, because that's where the end user was finding the problem. Data. Your tests need data to run. So you need to think about what should be your test data, what you expect to be your result, and whether when you get the results, whether those are actually your expected results or there's something different. Okay, now there's lots of sort of erroneous conditions that can happen. One I want to mention to you particularly, that you should check for is how you want to handle floating point numbers. Never, ever check for equality on floating point numbers. Computers do not handle decimal floating point numbers properly. If you add 0.1 10 times, you do not end up with 1.0. You just don't. So for floating point numbers, you want to check something about in a range. And other things here you can sort of look at it, and then you might want to check, whether the lists are in the order you want or not. And I will provide links to the slides as well. Of course, this is being on video. Another thing to think about is state. Many systems, particularly if you're working in certain types of applications like that are physical systems, like say motors or stoplights in this case, or elevator controls or whatever, will have states that change from one to another. A transition table is a useful thing for thinking about how those states change. And with that, we can take that and then just plug it straight into a test. Now here's an example in RSpec, a Ruby testing tool, where we have our stoplight and we set it at green. We expect it to go to yellow. Our action is that we switch it and then we check that it actually is yellow. Booleans can be an interesting challenge. We want to test only critical combinations. Now here's an example. In the state of Maryland, to drive under a learner's permit and to be legal, not only do you have to have your learner's permit, which is kind of assumed, but you must not have your cell phone, use your cell phone in any way. So you need to really have it off. So it shouldn't be on. Also, you need to be accompanied as a passenger by a licensed driver who's over 21 and who has 3 years of experience driving as a licensed driver. Okay, so we basically got 4 Boolean conditions there. Now, if we put that together in some sort of a truth table, we have 16 possible combinations. If we had 5 Booleans, we would have 25 possible combinations, 6, 36, and so on. That gets unmanageable because it exponentially increases. But most of the time, we don't need to do that. So here, we only have one that's true, and we have only really 5 tests, because on certain parts of it, we don't care. If the cell phone is on, If it's true, then we know that we can't drive. If the passenger isn't licensed, then we know it's not okay to drive. If the passenger isn't at least 21, it's not okay to drive. If the passenger doesn't have 3 or more years of experience, it's not okay to drive. So we only really have 5 tests with a bunch of don't cares. I actually did learn about this technique as an undergrad, but I did not learn about it in computer science class. I learned about it with some of the double E's as we were putting together digital circuits and playing with digital logic. And we're working on trying to get the minimal number of circuits that we needed.
Camille, we have a question on the stream.
Yeah.
From Curious Agilist.
Hello, Curious Agilist.
How is BDD different from London style TDD, aka outside in or top down?
Okay. So yeah, there are 2 styles, and I tend to favor, as someone might notice, I tend to favor what I call Detroit style, because that's where it originally came from, the auto industry, and it's sometimes called Chicago style. And there's another style called London style. London style uses an awful lot of mocking. There are some things you have to mock, and we'll get to talking about mocking in a moment. But in that type of TDD, you basically mock out the things that you're interfacing with ahead of time, rather than doing it bottom up of creating little bits. And it depends what you're building as to whether or not you have a choice into what style. I will discuss mocking and mocking approaches in a little bit. Does that answer it enough for the moment?
I believe so. We're getting some comments on who's Detroit and who's London style right now.
Oh, okay. So London style is a top-down. We write basically a loose framework with the classes that, for instance, that we're going to build are stubbed out, and we'll talk about that, and using various types of test doubles, which we'll also talk about. In the Detroit or Chicago style, we do it the other way around. We build it up from the lowest level of code, and then we build the other pieces of software on top of it. Both of them use automated tests to drive things. Anyway, here are the tests themselves. Another thing that is worth knowing about is on, off, in, and out. And that is when we're looking at boundaries. So something is on point, the value is on the boundary. If it's off, it's not on the boundary. If it's in, it's within it. And it's out, it's outside of it. This is just, again, a way to think about your data that you're checking against. So if we have a number line and we are looking for an integer between 5 and 15 inclusive, then the 5 and the 15 are on. The 6 to the 14 are in because they're inside the boundary. They're also off because they're not on. 0 to 4 and also 16 to 20 are outside and they're off. Now, again, another thing about floating point, because for floating point, there is no such thing as on. You're never exactly right. So always check something within boundaries. Now, funny thing that you should bring up the subject of mocking, because here's where we're going to start talking about it. We use something called test doubles. Think of that like in acting. In acting, you have a stunt double that takes the place of an expensive actor. In testing, there are other things that you will find expensive or difficult to use. directly. So their test doubles cover a variety of different things. And we're only going to talk about some of them here. Okay. I just wanted to check a double note here. So there are 4 types. There's dummies, fakes, stubs, and mocks. I'm not going to go into the details on that. You can read them. The reason I'm not going into details about all the different types of them is because most everybody just calls them mocks. They aren't all mocks, but that is one of the common phrases that are used for the different types of dummies, fakes, stubs, and mocks. Okay. So when should we use them? Well, if we're using London style, we're definitely using them. But we want to use them to test classes or other in isolation. So we use mocks or test doubles to do that. Remember that I said about how those unit tests ran lightning fast? The only reason they can run lightning fast is because they can run in isolation. So those unit tests are not talking to the database directly. They're using a mock to substitute for that. And this is where we only really want what the data from the database would be, and we know what it is. We want to simulate various kind of environmental factors. You don't want to have to force a network error by pulling a cable. You'd much rather have something that throws a network exception. And you can use a mock to simulate that. How many of you remember the Y2K problem?
Yep.
It's a couple of folks. Okay, some of the younger folks don't. But it was a problem that we had where a lot of different pieces of software were due to die because they only used 2-year dates. And that, like my byte boundary problem, they were about to roll over on midnight of the January 1st in 2000. Well, we don't want to have to set the system time directly by changing what it says in the clock on the computers we're running at that to January 1st. We want to mock that out. So think about an example here. Here's a nice one. Let's say that you're writing a computer game, and that computer game, remember I like playing Dungeons and Dragons, it rolls a 20-sided die. And in that game, if our player rolls a 15 or better, he hits the troll. Okay? We mock out the random dice generator to force it to be a 15, so we can now test what happens when the player hits the troll. Lots of other things like that you can do, but random number generators are definitely something you need to mock to test. So we seldom use mocks outside of unit testing. There are several places you should absolutely never use mocks, and that's when you need the real behavior, the full behavior, including going to the database and back or whatever it is of the thing that you're testing. So for instance, when you're doing smoke testing to make sure that all of your systems are alive and well, you're going to use the real thing. We will discuss smoke testing briefly also. Here's an example. In this class here, I'll have a something that checks what time of day it is. It uses a a helper method down there that calls the date function. And the date function uses the actual system time. And then it formats it and does various things. And normally I just want to return what that time is. But if it's actually noon, I want to say it's high noon. Okay. Now, how would I write tests for that? Well, I can use a tool with Java called and JUnit called Makito, and there's lots of other tools out there where I go out there and I create this, what we call a mock object, and I tell it what I want to have returned. Okay, so that mock is going to assert, I'm going to use that for it to recognize that when I'm running the assert equal, I want to check that the time actually produces what I want, because I'm going to pretend that the system time, the thing that was using that helper, is 10:23. And in the other case, I want to pretend that it's actually noon. We're using a 24-hour clock here. So I want to expect it to be high noon. And that's the kind of place where you'd use a mock. Now, something important to think about is, what do you do with legacy code? Ooh, it's a pain. It's hard to understand.
Camille, before we jump
What's
into
that?
this, can we have a question that just came up on
Sure.
Twitch.
What's that?
How do you avoid horrible verbosity in testing from Artie Gold?
Ask Artie what he means by horrible verbosity. He's currently typing. Well, while he's typing, I'll start talking about legacy code, and then you can get back to me after I've mentioned it a bit. Okay.
Unscannable code.
What? Oh, code that's tests that are hard to understand?
Unscannable.
Unscannable. Oh, okay. So you're not talking about the test code, you're talking about the code that's under test, the actual source code?
Basically just hard to read.
Hard to read. Okay, so that is a question on refactoring. And that is something, I mean, there's some rules of thumb you should have, and that is you want things to be readable. That's where some of our Sparrow Deck stuff that we got into previously comes in. We want names to be meaningful, and that's including for all code, including the tests. We want it to be clear. We want it to not need comments. We want things to be short, things that are shorter, easier to read. I can create a, we can do a session on that a little bit later, but that's probably longer than we can have for right now. But in short, the same rules that apply to code in refactoring to make it understandable and readable and small. You want your code to be small. That's one of the things. You want your names to be meaningful. You want them to be clear. And you need, if the code isn't, you need to refactor to get there. If it's legacy code, then you tend to start out with a mess. So with that mess, how do you fix it? Well, first of all, a definition of legacy code is one that doesn't have tests. That's almost certainly going to run into. So there was a session not long back on characterization tests that we did here at Canton Coders, and that was an excellent example. Going through the tennis kata. I'll show you another example of some of the things, but the first thing you need to do is to put tests around anything before you refactor it. But some of the code you don't need to touch. Did we get any further clarification? Whether it was, no? Okay.
Yeah, I think we're gonna jump on Zoom later and talk more about it.
Okay, sure, I'll be happy to discuss things. So you can't stop writing features, but you can't stop everything you're doing to write tests for a million lines of code. And the mess of code I was telling you about, that included the German networking code, among other things, we had 9 million lines of code. Not pretty. Most of it in assembly language, a bunch of it in C, some of it in Pascal. Pascal stuff was actually pretty clean. If the parts of the code work in the legacy and you never touch them, just don't. Don't worry about refactoring that mess. So here is an excellent source, Michael Feather's book on working with legacy code. Modify only the things that you need to, and we're going to need to write tests around it. In order to change something, we need to get tests around it to get it under control. And then it's safe to refactor and enhance. To do that, we need to figure out how we can break apart the code into pieces that are not dependent on each other. That's a non-trivial task. It takes sort of looking into the code. So here's the one of those cases where, unfortunately, you do have to do some white box looking at your code itself to figure out where to go next and to write the test. So we were working together in the Code Liberation Front a short while ago on the Gilded Rose Legacy Code, kata, and for refactoring. And this code looks messy. It's actually a whole lot worse than it looks. To change something is to break it. There is some documentation, but a lot of it is a little bit vague or out of date. The first thing we needed to do was put tests around it. And as we put tests around the code, we found that we could understand it a lot better. And understanding it a lot better was a real help. In an hour or two, we got tests around the whole thing. And then the following week, we actually refactored it for a couple of hours and got it really looking clean. In order to create those tests, we needed to do that in baby steps. And this is the approach you will need to do if you've got a great, big, horrible mess. You need to do it in baby steps. You need to put tests around it. We made one test work at a time. Now, when the code already exists, doing that is different than with test-driven development. With TDD, we start with a red test, where if everything fails. When we're doing characterization tests, we are assuming that the code works. And so we are writing tests that we expect to be green when we start. But once we've gotten that all, then we can progress. It's really important to know that we have covered all of the code. So this is where it can be really helpful to have code coverage. And we got to the point that we got every single line covered by a test. Once we got to the point, we really understood how the code worked. So it became a lot simpler to change, and not to mention a lot safer. We refactored it to the point that was really quite clean. And then it would have been easy. We didn't at this particular point, but it would have been easy to add a new feature. Another final type of test I want to mention to you today is, whoops, we're not doing code coverage yet, is something called a smoke test. And you may work with your DevOps team if you have a separate DevOps team about this. And that's a test that's in place. It's fairly lightweight. It just checks, are the things that you need in order to run your app actually there and working? So are your databases available? Is your network there? Are the sockets and ports and things that you need to talk to, are they accessible? Is your web server up? Are you using web services? Can you get into them? What about the credentials and login services? You know, your LDAP or whatever you're using. Your CI and source control ought to be running all the time, but you want to make sure that's there. Along with that, we need to make sure the source control is there because we're going to need to check it out in order to run the code and build it. And of course, is the app running? There may be other things depending on yours. Now, code coverage. The 3 types of code coverage, sometimes called C0, C1, and C2 for line, branch, and path. Let's look at a couple of examples. So every automated code coverage tool out there does at least line coverage, and that's checking, is this line of code touched by your tests? Many automated tests do, both open source and commercial versions, do what's called branch coverage. Don't always assume that the thing that says it does branch coverage does really full branch coverage, as I've been discovering recently. Here are a couple older versions of things that are out there, but you'll find a whole bunch of newer ones for languages that you're using. And that checks whether or not you have branches. And the third type is path coverage. And it does this horrible combinatoric things of trying to go through every single possible way through your code. There are only 2 cases I've ever heard of that had complete path coverage for a large application, which I believe was written in Ada, both Department of Defense projects. And it was extremely expensive. You're not likely to find anything practical to use for path coverage, although you can create some yourself. So line coverage would test whether or not each of those lines, and all of them, are in fact touched by some type of test. Now here we are checking it. Here we aren't. So this is something I recommend. Do not put the then part on the same line. Also a reason not to use the question mark operator for ternary conditions, because your coverage tools will not know what to do with that. They may pretend they do, but they won't. You will actually need to write tests that check that itself. So, put those on separate lines. White space is cheap.
Camille, we just got a question on Twitch, if I can jump in here.
Can do.
What about mutation testing?
Yeah, that's a type of test that I haven't talked about. So mutation testing is when you have your code written, and to some extent, you're kind of testing your tests. Is it goes in there and it takes your code and it changes it. For Java, there's a tool called Jekyll that does this, if I remember correctly. And I believe that for Ruby, there's a tool called Heckle. They're both free. And what it does is it goes in, and there are a whole bunch of things I have not had time to cover today because there's an awful lot to this. Matter of fact, if you can see this book? It's just on testing object-oriented systems, and that's old. There's lots of new stuff since then. So mutation testing goes in and it actually changes values and things in your code. And if your tests are good, your tests will recognize failure. And if they're not, they won't. So it sort of tests your tests. It's a cool technique. Did that answer the question enough, or at least given the time we have at the moment? That's probably a worth topic at some point.
Yeah, I think it did for me.
Okay. All righty.
That's good.
Okay. So here we have the branch coverage. Now here we've got that Boolean condition that I talked about, and with the the paths explosion. And they call this basis path simplification. There are other terms for it. As I say, I learned mine approach in Boolean logic. But it's basically a technique to check and make sure that you're catching those important paths that are right. And as I mentioned with that, you're not going to find an affordable test tool, and particularly not for a modern language, that's going to cover these automatically. And they will take, if you could, it would take a tedious amount of time to run it. Other questions?
I don't see any questions right now. We'll give a couple minutes, but I did get a comment from Advanced Persistent Redhead, who said, "This is so nice and clear and actionable, and I appreciate the many hours of making this simple and engaging."
Thank you. Well, that's really nice. As I say, there will be a video of this, and I will post these slides on SlideShare, so that you can actually look at some of this material, and maybe in another time we can go into some of these techniques or try something that we didn't talk about much here, like mutation testing at another time. There's a lot to know about testing. And testing should be just like writing the code itself. It's part of doing software development. And it's something they didn't teach you to any degree in computer science class.
Thanks, Camille. This was fantastic. The presentation was very good. I'm excited to watch it again, actually.
Thank you.
So we're going to put, are you able to stick around for a little bit?
Absolutely. If I might take a second to get something to drink, as my throat's getting a little sore.
Okay.
But, oh, and here's the contact information on me again. And how to find me on SlideShare. I'm Camille _Bell. And there's my LinkedIn approach. And if you want to connect, please do make a message that, you know, that where we met, i.e. you heard this and you're interested in things. And I try and get back to people. I'm not always as fast as I could be. But I really appreciate Canton Coders inviting me to speak, and you know, just love talking about testing, and hope you all will take some of this and make your lives easier because of it. Thank you very much.
Great, thanks, Camille. And we're going to put the Zoom link in our Slack channel, so anybody on Twitch can go ahead and get the link there.
Okay, great.
That wraps us up then.
Super. I will keep this up for a moment, and then I'll go on to Faces in a moment.
Okay.
On Zoom. Okay.